Yeah, can we have extra credit for showing up to class?
Well, if you keep doing that, you're gonna suffer at the very end, you know? I mean, because things pile up, you know, if you keep saying, well, it's just to finish up the class by 15 minutes early every day.
No, I said, can we have extra credit for showing up? What are you talking about? What are you talking about? Right? If only the shortcuts.
What?
If only there were shortcuts to college.
Yeah, right. My answer is yeah, right, yeah. Let's just take attendance. Okay, good.
It's a turtle.
I'm not good at it. I'm kind of realizing your avatar is turtle, your avatar is what is that? Really fish?
You never noticed before.
And
Wow.
I couldn't think of anything.
sorry. Do you wanna make avatar too? Well, it's not important, of course, because I know you. But
I mean, I could, but
do you have any idea of avatar?
no, not
Oh,
really.
okay. Yeah, it's just making fun of it. That's it. It's not important. Okay, now 4 people online. How's that? Everybody's doing okay? Raise your hand if you're doing okay. No one is raising a hand. Okay. People online, raise your hand if you're doing okay. That means you're not doing okay. Raise.
This one, this two.
Connor, are you online? Or you just logged in and watching TV? Or
Yes, hi. I'm
Okay,
struggling to
good.
figure out how to raise my hand. There we go. Now I'm figuring it out.
All right, good.
They changed the interface. It's now in like a sub menu to raise your hand. It's no longer just a simple button.
Yeah, because
Figured that out now.
Microsoft keeps changing those things. Yeah, I hate that, but I think they're trying to beat Zoom because Zoom is a Chinese software. I don't use it. Okay,
Chinese software?
Zoom.
Oh,
Well, yeah, it's a Chinese software. You know, there's a backdoor.
I thought it was, no, it's not.
No, I mean that's a Chinese software. Well, no,
No, it's not. Is it?
you get extracted all your data by using it.
Oh, yeah, but not.
Nowadays, I don't trust anybody. That's the problem, right? Okay.
You trust Microsoft?
Well, Microsoft is the only choice, least potentially harmful software.
Oh, okay, here you go. Just cleared up. Zoom is an American company founded by Chinese-American billionaire Eric
Yeah.
Yuan. So, I mean, technically American, but yeah, I mean.
It is Chinese.
American, so that's really.
Technically.
Bottom line is who's paying money for it?
Yeah.
Okay. So yeah. Anyways, it's not that I do trust Microsoft anyways, but it's a least harmful.
Microsoft does.
Okay. So today, let's just take a look at updates to begin with.
Microsoft does.
Here we go. So here's a new update, very fresh, brand new updates, Tuesday today. The due date for homework of Unit A2 and take-home quiz 4 are both postponed to 11 a.m. Thursday, February 25 due to multiple requests. Due to multiple requests is important. I'm not going to usually do postpone based on someone said, hey, could you postpone? If Jimmy says, please postpone, I say no. If Jessica says, please postpone because I'm so sick, I ate something wrong, I say no. But 2 people come in and say, well, you know, please, okay, now this multiple request. Too bad, I have to do it. Now I realize who's missing. Jessica is missing. So she's sick, okay, yeah. Okay. So anyways, homework A2 and quiz 4 are both due Thursday, okay? 11 a.m. Homework 2. What?
That was due today.
That was due today, supposed to be.
No, yeah.
Did you postpone that too?
Yeah,
Yeah, it's
yeah.
Oh.
You don't want to?
both of them.
If you don't want to, I can revert back to today's due.
It's already turned in.
It's already turned in.
It's
No,
already
it
turned
doesn't
in.
matter.
Yeah, that makes sense.
Okay, good.
Because I thought it was due.
That's what I thought, too, and I went on and like, what? Wait.
Well, no, well, basically, that's what I thought is not the discussion because everything's written here, so.
Did you
Well,
change
there's one
it?
Okay,
He changed it. He changed it.
everything is written in this class. Sorry for that. Well, that's what I thought. Well, no, sorry. Okay, so let's just get going today. I want to finish up Unit B1, which is wings and high lift devices. So today we are going to spend some time take a look at high lift devices. Of course, in your semester project, I would expect you to incorporate your high lift devices. High lift devices sizing is also another important thing to design your airplane, which I'll try to cover that. In other words, trim. Trim is, in order to sustain level flight, you probably need to have control surfaces to make it trim. Trim means you basically don't have any moment developed, so you can continue sustainable level flight. Sometimes, you have to deflect your control surface a little bit to trim. It's called trim angle of attack. Stuff like that. You can compute those things using the software. That's a great thing about Xflyer 5. Okay. And the whole aircraft is another category here because we've been talking about airfoil to begin with, which is a 2D cross-section of a wing. That is the starting point, of course. You're picking up and use the software, doing analysis for 2D cross-section airfoil to begin with, and you build the database. Then after you build the database, you're going to design your wing. The wing is an integrated effect of every single cross-section in a span-wise arrangement that is going to predict your performance of a 3D wing. And the next step is, of course, your airplane, of course, has more than just a wing, okay? Your airplane needs to have a tail if you want to make it stable. So we are going to talk about static stability and then stability margin and all that. So tail sizing is also another important thing. You can do it using this software. Okay, and then also horizontal and vertical tail both. And then depending on type of main wing, you may or you may not need stabilizing surfaces. We can talk about that. And then fuselage, of course, you can design and integrate the fuselage of your airplane, and then location of your propulsion system, such as if you pick up like a motor and then propeller, how heavy is that, where is the location of those, that is going to determine your distribution of your weight of your airplane. That is going to determine center of gravity. Then once you come up with the center of gravity and then location of your neutral point against that center of gravity is going to determine, again, the stability as an airplane. Neutral point location we are going to find out, okay, using the formula and theory based. And also neutral point, I think, not sure, but Xflyer 5 actually can compute that for you. And also center of gravity. So in other words, you can go all the way, starting from 2D design, all the way to the entire airplane with the stability analysis also. That means before you even put your hands on manufacturing of airplanes, you can use this software to design complete airplane, then you can tell this airplane is stable, at least statically. And also at the very end of the semester, I would want you to explore the dynamic stability. In other words, if you disturb the airplane has a tendency to go back to the original condition. And how long does it take? Does the oscillation keeps going or die down very quick? Dynamic stability. You can also do that. So we are going to explore the full details of this software called Xflyer 5, which is an amazing design tool of airplane. And then I see a huge potential of this software because no one really knows fully how to use it. There's absolutely no manual or anything. There's no explanation given by the software developer. They keep developing a new version, and then we have to find out by ourselves what's new. Okay? No manual, no nothing, and then it's impossible for you to master unless you know aerodynamics. That's the bottom line of the software. So if you have a mastery skill and understanding, that's a huge value. As a matter of fact, if you're trying to get a seriously airplane design job, this is a huge prize. At the job interview, you say, well, I have a mastery skill of Xflyer 5. Oh my goodness, really? How did you learn it? Well, because my professor is like a geek. You know, he just did it kind of thing. Not many people actually did this, and then there's absolutely no manual, no like a coordinate class for X-Flyer 5, no nothing. So the only people actually know this software is a developer, only 2 people. Okay? Dorera Yagrin, that's it. One is MIT professor, the other one is a student for him. That's it. Interesting. So come to think about seriously, if you are an enthusiast of airplane design, this is a fun class, hopefully, and then you pick up lots of skill set along with it. Most of the skill set you can pick up is based on exploring by yourself, okay? So anyways, let's move on. So today, I think we stopped at somewhere. I think where did I stop? I think we did the page 7, right? In last class, example B11. This is a finite wing, okay? Finite wing. And then finite wing is designed based on the airfoil. And then now you are computing how much lift and drag is developed for this finite wing. And then you compare it against 2D wind tunnel test, which is a quasi 2D wind tunnel test, which determines the section lift and drag coefficients. And we compared together, and then we realize once you make your wing, obviously your performance is going to deteriorate. Lots of factors, but one of them is you're going to basically lose the lift curve slope because of the presence of downwash due to wingtip policies. That's a big thing, okay? So in order to create the same amount of lift coefficient, you really have to have higher angle of attack. And because you lose that, in order to have the same amount of lift produced for entire wing, you have to increase the wing area. Nothing is good. So that is the design of a 3D finite wing. So of course, 3D finite wing is based on the 2D airfoil analysis. But you need to understand, once you create the wing, all sorts of 3D effects come into play. Most of them basically is an adverse effect. So you hoped, based on the 2D analysis, you hoped this much lift coefficient, but you never get it. It's going to be always less than that. Okay. So this is, okay, so let me just add a few notes here at the end of this page here, okay? So I want to emphasize a few things, okay? So we talked about 2D airfoil. So this is your starting point. Now you looked at, based on the 2D airfoil cross-section, you're going to design 3D wing. Okay. So this is a this performance. So today, one more step. What is it? Whole aircraft. Here we go. Okay. So one more step is entire aircraft. Again, this is less performance. Because entire aircraft, the whole airplane, is composed of many things, such as tail, surfaces, and then landing gear, and lots of unnecessary stuff, purely speaking, aerodynamically speaking. You have to add all of those things. Antennas, and then wires, and then something, perovskite tube, and stuff like that. Surface is not that smooth, and then you're going to add more drags. As you add more, you're going to lose your lift, okay? So that's something we need to look at it. There is a unit, I think unit B3, I hope. B3, yeah. There's a unit dedicated to actually estimate whole aircraft performance. Everything is entirely hand calculation. This is a classic method to determine whole aircraft performance. Now, one beauty of the X-Flyer 5 is, using that software, you are actually designing the entire airplane. And you can actually come up with the entire airplane performance using X-Flyer 5. So one of the project phases I'm thinking right now is I'm going to force you to use X-Flyer 5 doing whole airplane analysis. Come up with the whole airplane lift, drag, moment coefficient, center of gravity, other things. Then you're going to compare against hand calculation predictions. So you have to sacrifice one member out of your team doing entirely hand calculation. That sucks, but somebody needs to do it. So you basically, I don't know, you just do a poker or something and pick someone who needs to do entirely hand calculation of your airplane. Then compare against software results. Okay? I know you don't like it, but this is entirely necessary because the hand calculation actually reveals step-by-step theoretical way of calculating those things. If this class is taught by Dr. Ashworth, hand calculation is the only thing you can do. Okay, so it's a big difference here is I'm a computer geek, I'm using X-Flyer 5. But somebody needs to do still hand calculation, sorry. Okay, so let's move on, next page. So today's subject is high lift devices. You need to put high lift devices almost always, actually always, not almost. High lift devices are the device that, okay, what is the purpose? Temporarily increase the lift, that's it. Because when you take off, when you try to touch down, the demand comes in. You have to slow down the airplane to nicely touch down, feather touch landing. You have to slow down your airplane. You have to temporarily deploy high lift devices to minimize your stall speed. In other words, increase CL max. I think we talked about that in Aero 1. So this is the big purpose why you want to have flap. If you deploy the flap, you are going to temporarily increase CL max. If the CL max is increased, the greatest thing about that is you can slow down your airplane and your airplane can still fly. So stall speed is going to be decreased. Okay, that's the whole point. Okay. However, this actually comes with cost. The biggest cost is, of course, it comes with increased drag. CD goes up at the same time. And then obviously, if you deploy the flap, even though your basic section is completely symmetric, you're actually adding the camber by deploying any type of flap. What does flap do? Physically speaking, you're going to actually add the camber. Adding the camber really is the shifting CD0, which is a zero lift drag coefficient spot, to the right. So this is a CD0. CD0 shifts. In other words, same as if you have a camber. If you have a cambered airplane, CD0 doesn't occur at here. It is going to be shifted. In other words, minimum drag location is not the location of lift is equal to 0. Okay. So that's one thing. And also overall drag coefficient increase. Another thing is alpha stall. Angle of attack of the stall point is going to be decreased. Okay. So it's much easier to stall out if you fully deploy the high lift device and pitch up violently. Your airplane stalls very easily. So those are the things you have to pay the penalty of it. However, at the same time, greatest benefit is, of course, increase of CL max. Okay, this is what you need. Okay, so let's just take a look at the few different types of trailing edge flaps to begin with. Of course, we have a leading edge flaps too, but the trailing edge flaps, you have a plane flap, split flap, slotted flap, Fowler flap. Do you guys remember those things from Aero? Let's just take a look at the documents. Do you remember those?
You didn't do Fowler flap.
Well, I mean, I showed you a document. Bold method guys. I love those people. Good pilots. Let's just take a look at flaps. Here we go. So this is a document coming straight from Air1. Let's just take a look. So 4 different types of aircraft flaps. This is explanation provided by airplane pilots. Both method is just basically training school of airplane pilots. So this is how they explain the flap system. Flaps, making your wing more versatile. Flaps help your wing adapt to your current phase of flight. Current phase means takeoff, landing, cruising, other things. Are you taking off or landing? Extending your flaps increases lift and allows you to fly at slower speeds. That's the big thing, of course. Are you cruising at altitude? You're not going to use flap for that because you're going to increase your drag. Detracting flaps reduces lift and in turn decreases drag. Okay, so this is the clean configuration, something called flaps up. Normally, your airplane comes with a slight camber, so this is normal situation. So suppose you have a wing cross-section with a slightly cambered. Okay, so this is cambered airplane, clean configuration at the cruising. You're going to fly like this. Now, if you deploy a simple flap, this is a simple flap. You are going to actually increase the camber. Okay. As a result, you are going to increase the lift coefficient maximum value, CL max, at the same time, you're going to introduce the drag, more drag. Okay? So this is a plain flap, first of all. So it's a very simple flap, just a trailing edge, about 20% of the code is going to be deflected downwards with an angle. In this case, this is a really high angle. This is like a 60, 70 degrees deflected plane flap, okay? I'm not sure what this airplane really is. Probably a racer, Reno racer. World War II airplane based, maybe. I don't know what airplane it is. But, so this is the plane flaps. If you extend it, you are going to purposefully induce the flow separation on top surface and creating huge amount of wake. That means a massive increase of drag and then very turbulent flow behind the wing. But as a result, okay, you are going to increase the camber with lots of penalty of drag increase. Okay, so this is a plane flap. It's a very simple idea. And then some of the NACA standard airfoil test results, okay, NACA chart, actually certainly includes some of those data sets. Let's just find out. Okay, so if you go to NACA conventional airfoil data, some of them are associated with flap data. Not this one. Not this one. Here we go. This one actually comes with a flap data, right? It looks like a 20% of the trailing edge is deflected 60 degrees. As a result, this is the drag polar. So this is a drag polar with a flap deployed. This is a lift curve with a flap deployed. This is the quote-unquote moment coefficient with a flap deployed. Obviously, you can tell so many things by looking at this data. If you deploy the flap, you can temporarily increase the CL max here. Of course, that's a great benefit. But at the same time, increase the drag polar. In other words, overall drag coefficient goes up. And then also, whoa, you have a huge tendency of pitch down of airplane. You have to compensate it, right? So when you deploy the flap, you have to compensate the developed pitch down tendency of the moment. So that is a trim. In other words, trimming is also the purpose of this control surface. If you deploy the flap, your airplane starts to try to pitch down. You have to pitch up by counteract with it. Okay, that's called trim. We're going to cover that later. Okay, so now, where is it? Oh, okay, this one. So this is the plane flap. And then idea here is, well, you know, I don't want to have lots of induced flow separation wake, so let's just deploy only bottom half of it. It's called the split flap. This is a common choice for World War II airplanes. Split flap is basically retain the top surface, but only deploy the bottom. It's completely split. So this is a split flap. You're going to retain the top surface, so you're going to minimize the flow separation and the wake, but at the same time, you're going to effectively increase your camber. So this is actually much more efficient compared against plain flap. Okay. Number 3 is a slotted flap. Okay. Typical choice for like today's smaller scale business jet type of thing. Slotted flap introduce the slot. So you're going to purposefully introduce portion of the flow going through this slot. If the flow is going through the slot, it is going to accelerate. Okay. So here we go. So you're going to introduce high pressure accelerated flow over the top surface of this flap. That is going to completely prevent the flow separation. So the flow is much more cleaner compared against other 2 different types of flaps. Okay. So this is going to actually induce the reattachment of the flow over the surface of the flap. So efficiency goes up for the flap. And then, of course, if you take a flight to go back home, this is not the airplane cross section, right? Have you ever have you ever sit right next to the wing when you go home? And then right before the final landing approach, can you take a look at the wing? Then people say, oh my goodness, this is so dirty. I can see almost everything. Yeah, that's Fowler flaps. Here we go. Okay. So Fowler, the name means that you are actually stretch out the area. Stretch out the area. So wing area is going to be increased at the same time of camber. So this is the Fowler flap. So this is a double slotted Fowler. Not only you include those slots, at the same time you're going to stretch out the trailing edge so that now your entire wing area is bigger. At the same time, camber is increased. And also you introduce the slots, so accelerated high pressure flow flowing over the surface of those flaps, preventing flow separation. So today's jet airplanes, by employing this Fowler flaps, you can actually really slow down your airplane amazingly. There is a flight simulator in my research lab, and then there is a one airplane which is Airbus A380 in a smaller scale, radio control type. You can actually fly in the simulator, and then you'll be amazed how much you can slow down. My goodness, it's almost stopping in air. It's like you can slow down that big airplane just like that using this type of Fowler flaps. Okay, it's kind of fun, flying those things in computer simulation, flight simulator, and you can really slow down that airplane. Okay, still flying. Okay, so that's the 4 different types of flaps. I think we covered it in Aero 1, but also here today. So let's go back to Unit B1. So those are the plain flap, split flap, slotted flap, and Fowler flap. And also there's also one animation of Fowler flap. Okay, let's take a look. So this is the mechanism. Oh, equals F5. So interesting.
I don't know if it says that I'm a big nerd or not, but I've seen this video before.
This is how Cool. So if I end up teaching senior design, I'm going to probably force students to, okay, come up with something like this, especially structures guys.
Dr. H,
And then aero guys, you guys basically become a master of X-Flyer 5 and design everything in computer and then come up with the performance prediction before you even build it. And then how much performance prediction and the actual performance difference is going to be your grade kind of thing. Yeah, if the performance is like rest 50%, you fail. Too bad. You have to repeat this question again and again. Just kidding. I can never do such a thing. So anyways, that's the high lift devices. So obviously high lift device design and sizing is going to be included in this project this semester. Don't worry too much about it because you can find out easily that the X-Flyer 5 actually integrate those high lift devices and control surfaces into it, and then you can actually compute and predict. It's really fun thing to do, okay? Because if you do everything by hand, it's a nightmare, of course. Using software, you can probably do it in a few hours, at least, okay? And also another thing is some of the airplanes comes with the naturally attached strakes and leading edge extension, LEX. This is the additional control surfaces, for example. Here we go. This is F-16, actually have strakes, and then FA-18 Hornets have a leading edge extension that is actually going to create vortices created at the tip of the strakes. That vortices is going to impinging into your main wing, actually adding more lift to it. It's called the delta wingtip vortices. Have you ever seen that in aero? Have you? Do you want to take a look at it in aero? Delta wing, okay. So if you go to aero page, delta wing. Delta wing. It could be handout, sorry. Yeah, this one. No? No. Yeah, here you go. So delta wing. So the idea of leading edge extension is delta wing actually creates the twin pair of vortices. This vortices actually create the rift. It's a vortex rift. So your idea is basically creating those two vortices, just like a delta wing, apex vortices. And those straight vortices actually add up some lift to your main lift of the wing. Okay. And then there's a way to estimate those additional lift created by strike vortex, which I'm going to cover that in I think unit B3. Okay.
There's no downwash from those vortices?
No. It's just a pure, this kind of flow field itself actually creates a rift. Vortex rift, something called. Obviously, yeah, it's a good point. Of course, if you have a vortex like this, it is going to add more of the downwash. So your main wing is placed already inside of the downwash of those twin vortices. But this vortex is going to have, suppose if you pitch up, vortex is going to come like this. Pitch down, it's going to still come like this. It's fairly parallel to the incoming flow. So it is going to actually creates the steady lift coefficient for all range of angle of attack, especially high angle of attack. That is quite important. It is going to be additional lift for high angle of attack, because main wing cannot create the lift at the really high angle of attack. You can't do that. But suppose if you have that kind of surface, especially beneficial for like a fighter airplane like this, it is going to support the lift at the very high angle of attack. Okay. Now back in like the 1990s. I was a student, graduate student, and then we watched one of the air shows in Moscow, and then that was the brand new Russian airplane, Su-27 came into play. That airplane comes with this strake and also actually canard in the forward surfaces. And one of the performance demonstration of that Su-27 new version was Cobra maneuver. Do you know Cobra maneuver? Airplane flying in like this, pitch up beyond the 90 degrees, and pitch down and fly like nothing happened. It's called Cobra maneuver. And then everybody says, oh my goodness, what's going on? How can you do such a thing? Oh, because of this. Okay. It's a vortex additional lift. Okay. Without, without those straight surfaces or canard surface, you can never fly like that. Regular airplane configuration cannot support the lift beyond 90 degrees. No, you can't do that, right? Of course, it's beyond stall, but Su-27 was able to do that. And then blasted all the graduate students watching that, air show. I was there too. And then we brought up that discussion into the classroom, and professor and students actually they started to argue. Oh, they're faking, Russians are faking that. No, it's not. Anyways, Cobra maneuver, that's the pretty interesting maneuvering. Okay, a little bit more on high lift devices here. Of course, you can have a leading edge flap. It's called the slots. You're going to create the gap in leading edge. You're going to introduce the flow through it, okay? This is called slot. This is called fixed slot. This is a slot. Now, some of the airplanes you took, like probably Airbus, they have leading edge devices just like this, okay? And also a few more things, like this is called internally blown flap. You are going to purposefully introduce the engine bleed air and hitting on the surface. This is called internally blown flap. This one is externally blown flap. You purposely place your flap or high lift devices inside of the wake of the jet engine so that you are going to use the jet hot gas exhaust hitting on the surface. This is the upper surface blowing. This is, by the way, the technique used for the airplane sitting right next to the bookstore. With this kind of wing, how can you slow down your airplane? You need to have some kind of gimmick just like this. This is called upper surface blowing. In other words, engine bleed air is hitting on the surface of the flap system, preventing the flow separation. Okay. I mean, if you are designing low-speed airplane, you're not going to choose the wing like this shape, right? This is a horrendously bad airplane for low speed. Okay, so you have to do something. Okay. The other one is vectored thrust. Obviously, this is what F-35B, and also Harrier. It's a classical design of vectored thrust. Okay. All right. So let's just stop and take a look at this thing. Okay. So now, all of a sudden, right here, very suddenly, now I'm talking about whole aircraft. So whole aircraft means everything. Okay. So airfoil, 3D wing, plus all others. This is whole aircraft. So as you look at the entire aircraft, as you design it, it is very, very difficult if you do it entirely by hand, but you can do fairly easily using software. That's the beauty of using software. But anyways, you are going to define the entire aircraft drag pole. This is not something you can do easily by hand. You need to have a software just like X-Flyer 5. But after you put everything together, okay, you are going to choose your 2D cross-section, build the wing, put the fuselage and tail and control surfaces and other things. And then decide the location of your engine and propeller, and then put the mass distribution on it, landing gear, blah, blah, blah. Now you can pitch up and down your entire airplane to come up with whole airplane drag polar. You can do that in Xflyer 5. That's one of the greatest benefits of that software. Now, if you're designing by hand, this is near impossible. You can only guess, okay? So this is one of the greatest things you can do. So this is the whole aircraft drag polar. This is, by the way, polynomial function. So you can actually describe this as a polynomial function, okay? Now, important thing is two different kind of drags you can say. So one kind of drag, this is called parasite. Or this is zero lift drag, CDO. What does that really mean? Now, entire airplane is flying right now, and you are not producing any lift, zero lift. How much drag do you have? It is essentially composed of how much exposed surface do you have because of the skin friction and all that. You're going to have a parasite drag coefficient. This is called zero lift drag coefficient. And then as your airplane starts pitching up and producing the lift and more lift and more lift, as you produce your lift, you're going to start increasing your drag based on the lift. This is called induced drag or drag due to lift. Okay? So two different kinds of drag coefficient you need to consider. And then those two different kinds of drag coefficient can be represented by a polynomial function. And you can find out and squeeze out that polynomial function information using software. And then at this moment, you realize, hey, using this software, you can do something you can never do by hand, at least easily. Okay? So this is called the induced drag. Or this is drag due to lift. So interesting thing is, as you increase your drag, as you increase your lift, and more, you are going to also increase your drag. Too bad. Okay. So this is whole airplane. Interesting thing is this K factor. This K factor now includes something called E0. Okay. E0. This is called Oswald's efficiency factor because this is for entire airplane. Now, if you remember last class or class before that, we introduced you span efficiency factor E. You remember that? E is a span efficiency factor. This is for 3D wing. So as you design your wing, based on how good your design is, you're going to determine span efficiency factor of your designed wing. But after you put other things all together, creating the entire airplane, now you are going to have Oswald's efficiency factor. This is probably much lower than that, right? Because all other things come into play. Okay, so let's differentiate. E is a span efficiency for 3D wing. This is going to be even further reduced to Oswald's efficiency factor after you put everything together to make the entire airplane. Okay, let's be very careful about the terminology. I'm going to introduce you for a moment here. The handout. Okay, let's just take a look at the handout. Handout. Yeah, here. Handout B2A before you even get in B2. So this handout is quite important. Let's just take a look at it. So this actually summarizes, okay, all three differences. One is a 2D airfoil, the other one is 3D wing, last one is whole airplanes. Okay. This one-page document is so wonderful, so I decided to put it as a handout. Essentially, in order to understand the airplane aerodynamics, this is all you need. Okay, this is so good. I fell in love with it. So 2D airfoils, lift is basically 2D airfoil lift coefficient. So this is a prediction of lift coefficient. This is lift curve slope, usually 2 pi per radian. Of course, you know that. If you create the wing out of 2D cross section, obviously you're going to reduce the slope. And now this CL is a 3D wing lift coefficient. Now CL alpha is reduced from CL alpha. This is the equation, of course. Then suppose if you create the whole airplane, now everything is included, okay? So this is a CL alpha plot. And then now you have to think about load factor N. Okay, so load factor N we're going to talk about, right? Drag coefficient is more kind of complicated. So you begin with the drag polar for 2D profile. So 2D profile consists of two things, skin friction, pressure drag. And then skin friction drag is this much. Pressure drag is basically as you increase your lift, you're going to increase your drag. And then you can get all of those information from airfoil chart, NACA 4-digit, 5-digit, 6 series. You can look up and get those data sets here. However, if you design your 3D wing, obviously it's not going to be the same thing. Of course, span efficiency factor comes in here, KCL. This E is a span efficiency, right? So this is the wing's efficiency. And then CD is, this is the profile drag coefficient 2D data comes into play because basically CD doesn't change. Pressure drag is different. I mean, yeah, that's right. Skin friction drag doesn't change from 2D to 3D. However, for the 3D wing, of course, you're going to have more drag, obviously. Okay. And then how worst, I mean, how much you can make it worse is going to be how well you design your wing. Yeah, the span efficiency could be really low if you do a poor job. If so, your airplane ended up having less lift, more drag, which is terrible. And people say, hey, this airplane sucks. That's what it is. Because you did a poor job designing wing. So wing design is also one thing which is quite important. You have to play lots of factors, changing factors, and then design it and compare against it. You have to go through that process. You know, if you only do it by hand, you can only do certain things. But this software, Xflyer 5, you can play lots of things and compare against. So that is the phase 2 of the project we're going to talk about today. Okay. And then entire airplane. Obviously, now you are going to introduce Oswald's efficiency factor right here. This is even worse than that. Okay, so this is going to be even worse because entire airplane now come into play. Okay, so this CDO is a parasite drag coefficient, or sometimes called zero lift drag coefficient. Okay, so now you have an entire airplane drag polar, entire airplane. This is what? CDO, CL square CD, slope is K. Yeah, this is basically induced drag coefficient plot. So this is the CL alpha plot for entire airplane. Now, usually entire airplane, zero angle of attack is zero lift, typically, because when you design your airplane, if you don't pitch up, you don't want to create any lift. If you put the camber, obviously you're going to introduce alpha zero lift, but that's essentially the subject of the wing. As you design your actual airplane, alpha zero lift is usually zero. Okay. So lots of differences. Do not get confused. It's so easy to get confused between this CL to this CL to that CL. Those are all different. And also at the same time, this CD to this CD to this CD. Those are all different. You have to differentiate all of those three differences. One is airfoil, one is wing, one is whole airplane. Okay? All right. Let's take a look at page 10, example B12, whole aircraft lift and drag. Okay. So let's think about the Avro Balkan jet bomber. Have you ever seen this? Do you know what the Avro Balkan is? Let's Google and find out. Avro Balkan. Here we go. So this kind of airplane, here we go. Why this airplane is chosen? Because it almost looks like just a wing, little bit of fuselage. Okay, and then this is interesting. It's not quite delta wing. It's like a delta shape, but you have like a finite code at the tip. But there's no tail, right? So this is a classic design of tailless delta wing. You can actually make it stable without the horizontal tail. Okay, tailless delta. How's that? People still make this kind of airplane, like the people in France still make this kind of airplane. Mirage. Okay. All right, so this is Avro Balkan. So the Avro Balkan jet bomber aircraft is nearly an all-wing airplane with only a small fuselage section sticking forward of its large triangular-shaped or delta wing. Its wing uses a thin NECA 0009 airfoil. I don't think this is correct, but let's just follow through it. Its wing uses a thin NECA 0009 airfoil. This is the symmetric cross-section, 9% maximum thickness at the quarter code, NECA standard 4-digit. And has a wingspan of 111 feet and planform area of 3,964 feet square. That's a huge planform. Okay. Assume that it's flying in standard 5,000 atmospheric condition. So let's assume 5,000 feet standard atmosphere. True airspeed of 300 feet per second. Angle of attack 8 degrees. Now, interestingly, its CDO is 0.009. This is given. Quite interestingly, you can never get this information unless you design and analyze it as a 3D entire airplane, okay? Entire airplane. Because this is the parasite coefficient of the whole airplane. Now, if you design everything by hand, this kind of information can only be gotten by actual testing, flight test. Okay, so anyway, so this is given. Span efficiency factor, 0.9. This is E, isn't it? So this is only for wing, not the entire airplane. So wing has a span efficiency 0.9. Oswald's efficiency 0.7. This is entire airplane, E0. This is whole aircraft. Okay. So let's notice the difference. One is a span efficiency, which is a wing only. This is the whole aircraft Oswald's efficiency factor, which is really less than that. Average wing code, 36 feet. Let's call that C over bar average code. Obviously, the wing is not a rectangular wing. It's almost triangular, so you have to take the average value of code. So let's estimate how much lift and drag it's making for those conditions. So this is 8 degrees angle of attack, true airspeed 300 feet per second, standard 5,000 feet altitude. Okay. So what is the first step, you think? E. What is the very first thing you want to do? Let's find out Reynolds number. Reynolds number, and based on 5,000 feet standard altitude. Okay, so let's just find out. So flight condition Reynolds number is density, velocity, code length divided by viscosity. So I'm going to plug in all 5,000 feet standard. Density at 5,000 feet standard day 0.002048 slugs per cubic foot. This is standard 5,000 feet value. Velocity or airspeed, true airspeed is given 300 feet per second. Code length average 36 feet. Okay, this is average. Viscosity at the standard 5,000 feet altitude 0.0000 0.0000 3637. 0.00003637. This is weird small number because we stick with standard units, slugs per foot second. Okay. So some of the NX people don't want to use this kind of weird small number, so that's why they use pound mass. But you have to combine anyways, right? Okay, so if you compute that, you should get Reynolds number 60 times 10 to 6. This is very high Reynolds number. And then if you try to look up NACA 0009 chart data, which we have, there's no data set corresponding to this high Reynolds number. Let's just take a look at the homepage once again. Okay. So if you go to here, NACA conventional airfoil data, NACA 0009. Here we go. So this is the NACA 0009. The highest Reynolds number you can have is 9 times 10 to 6. This is the highest value. In this case, Reynolds number is 60 times 10 to 6. Okay, so order of magnitude lower data is available. This is the highest Reynolds number, 9 times 10 to 6. This is the highest Reynolds number available out of this data set. And this is your Reynolds number. Okay? So the problem. The problem. Okay. NACA 0009 data set. Highest Reynolds number is only 9 times 10 to 6. Can you still use this data? Somewhat, yes. You know why? Because you have to understand for higher Reynolds number, is it the beneficial or adverse effect? Let's just go back and take a look at it. So if the Reynolds number is higher, what happens? Reynolds number effects. Did I cover that? Did I cover that? For higher Reynolds number, what happens? Wait. Yeah, higher lift coefficient and where is it? Oh, it must be unit A2 or something. Do you remember those? Is it good or bad to have a higher Reynolds number? It's good usually. Let's just remember, okay? Okay, so one more time. So let's just go back to the notes of probably A1 or A2. I'm not sure. Note A2 maybe. So what is the Reynolds number effects? Here we go. No, this is effects. Okay. This one, okay, here we go. Reynolds number effect. If the Reynolds number is higher, usually a very good effect on lift. You're going to expect more lift. How about drag, which is also good? Higher Reynolds number is like a less increase of a drag for higher lift coefficient. Both favorable. Okay. So suppose if you are looking at NACA 0009, the data set highest Reynolds number given is 9 times 10 to 6, which is this data set, right? That is usually the lowest possible drag polar. So for higher Reynolds number, what do you expect? You're going to probably expect this kind of plot, right? This kind of plot. Okay? So it's not so bad using this data set. Actually, this is a conservative estimate. How about the lift? Of course, lift is almost unchanged for any Reynolds number. But here's the highest Reynolds number. You are going to actually increase the rift. So as a reality, I mean, you can expect this kind of thing, but you never know. But of course, you can use this data set as a conservative estimate, right? So that's what we're going to do. Okay. Okay, so let's just go back. So this is the Reynolds number. So you're going to actually pick up this Reynolds number out of given NACA data because this is conservative estimate. Okay. So first of all, this is the symmetric airfoil. Because this is symmetric airfoil, alpha zero rift is equal to 0. Okay? Alpha zero rift is 0. Let's just double check. Alpha zero rift is 0 right here. Okay? So if you do not pitch up, you're not going to have a rift. Alpha zero rift is 0 right here. If you put the camber, of course, everything shifted to the left. So you are going to have alpha zero rift shows up some small negative value. But in this case, it's 0. Next thing, let's just read off. If alpha equal to 8 degrees, what is the CL? Somebody please tell me. Maybe somebody online, I don't know, because they might be sleeping. So what's the value? Please give me. People online, give me a value. NACA 0009, alpha equal to 8 degrees, what's CL? Are you awake? Hello? Oh, Connor, go ahead.
Oh, no, I'm still looking at the chart. I just was raising my hand to show that I'm awake.
Sorry. Sorry about that. I muted you. Go ahead, once again.
Oh, yeah, I was just raising my hand to show that I was awake. I'm still looking at the chart.
Okay. So, anybody? What's CL?
Dr. H, I'd also said before, I don't know if it made me a super nerd, but the video of the flap that you showed earlier, I'd seen before class.
Yeah. Of course, it's coming straight from Aero. You took my Aero last semester, so you kind of remember. Okay, so 8 degrees, right here. Right here. No, it's not quite 1. No, it's not quite 9 yet. I would say 0.85. 0.85. No, it's not quite 0.9 yet. This is the value given from textbook authors, Air Force Academy people say 0.85. So let's use it. Okay. So let's estimate. Next step is CL alpha. This is the lift curve slope of this NACA 0009 airfoil under this Reynolds number. So what you do is basically delta CL over delta alpha. Typical choice is you're going to pick up 8 degrees of alpha, and this is alpha zero rift. Okay, this is alpha zero rift. Alpha zero rift means 0 is a CL. 8 degrees, you picked up 0.85. So this is going to compute 0.106 per degree. Okay. Now, if this is aircraft, I'm going to convert it to per radian, but I'm going to use per degree as is because this is flight mechanics. Okay. So next is dynamic pressure Q. This is 1/2 rho B squared. So this is 1/2 density is given 0.002048 slugs cubic foot. Velocity is 300 feet per second. This thing is square. Dynamic pressure is 92.16 pound per feet squared. This is PSF. Okay. This is dynamic pressure. Next is aspect ratio. Let's find out aspect ratio of the wing. This is going to be wingspan squared divided by wing platform area S. Wingspan is given 111 feet. This thing squared divided by wing platform is 3,964 feet squared. This is going to give you aspect ratio 3.1. Wow, this is pretty low aspect ratio wing. Of course, it's almost delta. Okay. So out of this information of the actual wing, you're going to now determine CL alpha. This is the lift curve slope of the wing. Of course, you know the equation, right? This is the CL alpha divided by 1 plus 57.3 CL alpha pi times E times aspect ratio. Important thing, a big difference from aerodynamics is this 57.3 comes into play because I just keep using degrees as an angle. So this is a conversion factor. If CL alpha is in per degree, you have to insert 57.3. This is conversion from degrees to radian. Okay, so I'm going to use the per degree value. CL alpha 0.106 per degree. And then 1 plus 57.3 times 0.106 per degree divided by pi. E is a span efficiency, which is wing efficiency, 0.9. Aspect ratio, we found 3.1. This is going to give you 0.0626 per degree. So you need to realize that this value, 0.0626 per degree, is very much reduced, right? So 2D airfoil has this is a lift curve slope 0.106 per degree. Now this is going to be reduced to 0.0626 per degree for wing. Reduced. Yes, big time. And then this is the low aspect ratio wing. Its reduction is pretty steep. Okay. Now next step is based on that information, you're going to predict the lift CL of the wing. CL of the wing is CL times alpha minus alpha 0 lift. CL, no, it's not CL, CL alpha, sorry. CL alpha times CL, yeah, that's a typo, sorry about that. CL alpha, alpha minus alpha 0 lift. So this is 0.0626 per degree multiplied by 8 degrees minus alpha 0 lift is 0 degrees. So this is going to predict 0.5 CL. Oops, 5 more minutes. So this is CL of a wing at angle of attack 8 degrees. So let's compare this value against this value original, which is 0.85. So this NACA 0009 airfoil expected to have lift coefficient 0.85 at the 8 degrees angle of attack. Now after you create the wing, you only expect 0.5 reduced, right? Oh my goodness, everything is reduced. So your wing design, airplane design is how much reduction minimized, okay? So that's the best design. So next step is, let's find out the drag coefficient. Okay. So drag coefficient is CD. This is going to be CD0 plus K times CL squared. This is whole aircraft. So this means that this is CD0 plus CL squared over pi times E0 aspect ratio. So let's be careful about that. So now the Oswald's efficiency factor comes into play. Okay, so let's just plug in the value. So if you plug in the value, you have a CL, which is 0.5, this thing square. Pi times Oswald's is now given 0.7. This is much, much less value than wingspan efficiency, right? Aspect ratio 3.1 still. So this is going to be drag coefficient of the entire aircraft 0.0457. So now the lift and drag. For whole aircraft. Of course, you can compute. So lift is equal to lift coefficient of the whole aircraft, Q, dynamic pressure times wing area S. If you plug in those, this is going to be 182,989 pounds. How much drag do you have? This is the CDQS. This is going to be 16,695 pounds. Okay. So this is the lift and drag estimated for the entire airplane from the given information. Okay. Do you have any question? Let's stop here today. This is the end of unit B1. So next class, we are going to pick up from unit B2. Okay. And then at the beginning of next class, let's just talk about the project phase 2. Documents up, actually phase 1B. Project phase 1B document is up, so please go ahead and start reading those documents. Okay. Have a good day and see you guys on Thursday. Do you have any question, people on right? If not, have a wonderful day. See you back on Thursday.